Hello everyone, welcome back to lecture 18, ECE350. In this lecture, we're going to talk about wave equations. That means we're going to develop wave equations. We're going to also talk about plane wave propagation in lossless media. And we're going to go through some vector calculus to develop relationship between electric field and magnetic field. In the last lecture, we have seen that we modified our Maxwell equation to come to this form over here. So we're going to use this form to develop a wave equation. So first take this equation over here, second one, and we're going to take the curl on both sides. If we take the curl on both sides, this one has a unique form right here. We have seen that in chapter 3 for Laplacian equation. So this form will give you this side over here. For this side over here, this is 0 because this comes from here. So this is 0, we only have this, right? So negative delta square E on from this side, so negative delta square E, right? On this side over here, we have j omega, negative j omega mu, and del cross h, and del cross h is basically this guy over, right? So I can multiply both over here and we'll find this one. So that would be omega square mu epsilon c e, right? So now if I bring them on the same side, that will be right. So that is your equation you got from Maxwell equation, and also using this identity vector calculus identity over here. And also let me tell you what is delta square is d square dx square d square dy square and d square dz square. That's your delta square. All right. So again, this is the delta square over here again on the slide over here. So now if I apply that to this equation over here, so this is the del square over here, and this is E, and on the other side we have seen that is become this one here in the last slide. So this is the same equation actually we developed in the last slide. So that's the same equation over here. Let's move forward. So this one over here is represented by a gamma squared. So that means your negative gamma squared, that means your del square E, negative gamma square E equal to 0. And same thing can be shown for this one here, gamma square H, sorry, del square H, negative gamma square H equal to 0. So that both, those are called wave equation for electric field and magnetic field. So your job is to try this one. We proved this one here, right? Your job is to try this one to find this, try this one. There's instruction in the book, all right? So for lossless media, as I said before, your sigma equal to 0, right? If your sigma 0, that means your epsilon become epsilon c, right? So now for lossless media, epsilon c could be replaced by epsilon, right? So that means also in the lossless media is a customary that you have a wave number k. So that means wave number k is omega square root of mu and epsilon. Mu is the permeability, epsilon is the permittivity, right? So then you can put it back here. You got plus k square delta square E plus k square E equal to 0, right? Where is gamma square equal to negative k square, all right? So k is the wave number. So now your E is a vector. It has an xyz component here, so xyz component here. So in your delta square E, it has xyz component here, and k square E has xyz component here. That should be equal to 0. That's the wave equation, right? The wave equation is what? Del square E plus k square E, right? That's your wave equation, right? So that equal to 0. That means here to satisfy this equation, each of the components should be 0, right? What I mean, to satisfy this equation, each of the component, it means that, let me go back here. So there are three different components: x component, y component, ey, ex, ez. You can separate them, right? So if I come over here, so if I take the ex out, I can separate that like this way, right? So that is 0. That means same way your ey, ez equation should be 0. So you can try that over here, how to write the equation for ey and ez in the same format. Each of them separate needs to be 0 to satisfy the equation, right? So let's work on this one here. Your job is to write EY, EG right here. I'm going to check them in the class when they come back. So over here, remember the plane wave, uniform plane wave has the same property on the XY plane, right? So it's propagating to the Z direction. This is the direction of propagation Z, and the XY plane here. So on this plane, they have the same property. So that means the value of E or H wave does not change on that plane. That means what that means. If you take the derivative with respect to x or with respect to y, that should be zero, right? Because they don't change. The same property everywhere. So if I apply that over here, so ex dx is zero. That means this component should be zero. Ex ey should be zero, right? So this component should be zero. Only component left is this one, and this one, right? So that is right here. What's happening? Why I cannot write? So that's right here. This 2 goes to 0 because xy plane the same property everywhere, right? So that is becomes this one right here. Okay. So this is only x component, right? So you can do the same thing for y component, and this should not be z component in there. Z component is not on the xy plane, so you can do the same equation, develop the same equation for y component there too, and also you can do the same thing for h in there too. All right. So with that, we can show that there is no z component on the xy plane. So we can show this one with some vector calculus. I'm going to do that in the class, so to get everyone involved in there. So hold on that one. We can show this one that EZ and EHG is zero. We're going to show that that means say that there's no component of electric field or magnetic field in the direction of propagation. All right. So let's go back to this one here. This is what we have seen, right? And this EX going in the direction of Z, right? So in the direction of Z is propagating in the direction of Z. It has two components. One go in the positive Z direction, one go in the negative Z direction. As I have seen in chapter 2, we used to call them incident and reflected wave. So there's two components. We're only interested on the positive Z component, direction component. That's this right one here. So if I now replace this one with only the positive Z direction component is right here. Okay, so it's only going into positive Z direction. All right, and it has his own direction. It's propagating to positive Z direction. The vector is in x direction over here. Okay. All right. So we're only talking about traveling along the positive Z direction, this wave here, and it has the vector direction in positive x direction. All right. So let's move forward here. Now, let's apply this, the Maxwell equation, modified Maxwell equation of this one into this waveform here. So is del cross E, it's a cross product here. Del is a vector, E is a vector, right? So if I do cross product with them, this XYZ, del is right here, and E is right here. E have only component in the Z, propagating in the Z direction, positive Z direction, right? Then, so that will become, if I do the cross product, that will become this one right here, right? On the right side over here, J omega mu, negative J omega mu, and H has three component here, so it's all over here, right? So now, if I equate the both side, you'll see that there's no X component on the left side, the X component is 0 here. Then Y, HY component over here, that's right here, so you can get that. That becomes this one here, right? Y is EXZ plus, we're only looking at the positive Z direction, so that's why I only take the positive Z direction component over here, okay? Then HG in the Z direction is equal to 0 because this is, remember that this is 0 because on the XY plane, nothing changed with the X and Y, so that is 0 over here, right? Derivative with respect to Y should be 0, that's equal to 0. So that means I have only this one here, bring it back here, that's the equation right here. And so if I take this this one here, right, as my HY0 what do you call it, positive, so magnitude of that, that means this one over here is basically, this whole magnitude over here is replaced by hy0a. This is the magnitude, actually. This is the magnitude over here, magnitude of the wave, and so that equation becomes this one here, right? So remember that this is the y component. This is the y component, right? It's in y direction, and so let's come back over here. So let's see here. So you applying this over here, you get hyg is basically hy0 exponential jkx. Again, is in positive z direction. This saying this is a positive z direction over here, and this one over here, it's constant because it's a constant value. That is, from there, if we inverse that one, this is called eta. This is the eta over here. It's the intrinsic impedance of a lossless media. So that also can be represented by just mu and epsilon over here. So now your easy, the electric field going in the positive g direction is expressed by this and is x component, and from here, so we use that one in this equation over here and found that our magnetic field propagating in the positive g direction has the y component. So y hat, this is the magnitude over here. This is the magnitude over here, right? And you know the eta is right here, right? So then eta is intrinsic intrinsic impedance of the lossless media. So that is your H. So H and E, they're both going towards the positive z direction, but they're perpendicular to each other. One is x component, one is y component. They're perpendicular to each other. So now that's over here. Electric field and magnetic field of a plane wave are perpendicular to each other. That's what I'm saying. One is x component, one is y component, and both are perpendicular to the direction of travel. So both are going to z direction. So x and y both are perpendicular to z, and this is called TM, transverse electromagnetic field or wave. Now in time domain, if we go back to time domain now, EX0 is the magnitude plus is EX0, this is the reference angle over here, and in the phasor domain, we have seen in last slide, the phasor domain, if you come over here, is EX0, that's the magnitude, and this is with the phasor domain, right? Whole magnitude over here is the positive z direction component right here, and this is the reference angle with phi. The reference angle could be 0. Reference angle could be 0 if you start from the 0, right? So then with that, your phasor domain to time domain becomes x hat in an EX0 is a magnitude, and cosine omega minus kz, this is coming from, sorry, these two over here, these two are coming from your phasor. This one is the time frequency domain, frequency information, all right? And same with your h in y direction, and same here. So this is the reference angle. This is the angle this is the value coming from your positive g direction, and this is the omega t is the frequency information. So this is both are in time domain equation. So look at here. So if this is the E, this is your H, they are perpendicular to each other. So H in y, if E in x direction vector, H in y direction vector, and both are propagating in the k direction. In a time domain form over here. So if you look at that, your E, look at it, E is the sinusoidal wave here, is always changing in x direction, always changing in x direction, positive or negative, and propagating into the z direction. And your H, they're changing back and forth in your y direction and propagating to z direction. All right. So E and H both propagating to z direction, but they're perpendicular to each other. And for your wave velocity, we have seen it before. This is this equation we have seen in chapter 2, and also your lambda, which is your wave length, that is also here mu phi over f, and your intrinsic impedance is mu 0 over epsilon 0 if you have a lossless medium. All right. And we're going to do this problem in the class. So that's all for your lecture 18 ECE350.